you could get that from today's talk. Thank you.
Thank you. Thank you. Thank you, Litian. Thank you so much. So let's begin the talk with these kind remarks by Litian. So if I can have the, yes, there it is. Puzzles to Unravel the Universe is the name of this book. And I'm happy to present it here. Let me just use my... So math and physics have had a long, beautiful history of interaction over many thousands of years. And different civilizations have contributed to it. For example, the Greek mathematicians and philosophers tried to use mathematical symmetries to try to describe physics. Other scientists all over the world, China, India, Islamic countries, all contributed one way or the other. Science is a borderless adventure. For example, Biruni accurately measured the radius of the Earth many, many centuries ago. Another example, actually, is, before I show this, how many of you think that the atmosphere of the Earth, the height of the atmosphere, was measured in last century? How many of you think it was measured last century? Raise your hand. How many of you think it was measured 500 years ago? Raise your hand if you think so. How many of you think it was measured 1,000 years ago? Raise your hand. Okay, so actually, yes, indeed, the atmosphere's height was measured about 1,000 years ago, not by sending rockets into the space, but by simple geometry. And the idea was, if you lived here, you will see the sunset when the sun is here, but when the sun goes down, even though you don't see the sun directly, the sky is still not very dark. It takes a few hours or an hour or more for the sky to get dark. The idea is that the reason the sky is not dark is that the sun still gets to some part of the upper part of the atmosphere, and you can see that. So when the sun gets down here, then you cannot even see the upper atmosphere, it doesn't get the sun ray, and then it's really dark. So using how long it takes for the sky to get totally dark, you can estimate the height of the atmosphere giving the radius of the Earth, which had been measured beforehand. So this way, you can see a simple application of geometry to a question about the height of the atmosphere. Quite remarkable. My area of research is string theory, and the aim of the string theory is to unify fundamental forces and particles into one framework. It tries to describe the smallest and the largest things into one mathematical object, strings. So the idea is that when we talk about particles like quarks inside the nucleus, in secret they are actually extended objects like strings, but they are so tiny, it is hard to see that they look like a string. Strings interact with each other by two strings coming and joining and forming another string, or going backwards, one string going and splitting to two strings. It's a very geometric theory interactions, which describes all the interactions in nature, including gravity, interactions of electrons with each other, as well as strong forces and weak forces. This area is very mathematical, and it involves many abstract ideas. Dimension of a space is more than 3 dimensions of space at one time. In fact, in string theory, is 9 spatial dimensions at one time. The shape and size of the other tiny 6 dimensions affect what we see in our universe. We assume that they are tiny, and that's why we don't see them, these extra dimensions, in everyday life. To see them, we have to have a much stronger microscopes in order to see much smaller dimensions. Now, the strings can wrap around these tiny dimensions, and these lead to insights about how the black holes work in our space and how the beginning of the universe may look like. So what is the space that tiny spaces are? We don't exactly know. Here I'm drawing spheres to depict them. Many popular examples include the Calabi-Yau manifolds that mathematicians taught us about, including Yau. and they have been extremely important for our understanding of the physical world. Now, you might think that it's very difficult to understand physical principles without knowing a huge amount of background. However, the highly mathematical aspects of string theory is typical of many attempts to connect physics with reality. Math is always in the center of a lot of attempts to connect physical thoughts with reality. But the question is, can we illustrate the connection between physics and math in a simpler way? This idea was the motivation for the course that I started when my wife Afarin recommended that I take this seriously, to start a course about trying to use puzzles, simple mathematical puzzles, to explain physical laws. Mathematical puzzles do not need much background. Nevertheless, they teach us something about the fundamental laws if we look at them carefully and clearly. So here, this kind of ideas led to this course that I teach at Harvard, and it led to the book that I wrote, Puzzles to Unravel the Universe. So this class that I taught had 12 to 15 students, and it is my favorite course to teach at Harvard. I'm going to teach it again in a couple months. So here, I'm going to give you examples of these puzzles that I share in this class with my students. But the difference is that I want to ask you to solve the puzzles. So you're going to help solve the puzzles. You're going to answer yes or no, and in this way, we'll try to solve the puzzle. So are you ready? Good. This is the English version of that same book. Okay, I'm going to have various topics. The first topic is symmetry and conservation law. Symmetry is very important in physics. Now, symmetry might sound boring, like if you have a triangle which has equal sides, you say, okay, there's a symmetry in this triangle of reflection, let's say. But symmetry principle turns out to be very powerful, especially when you combine it with conservation. Conservation, that things don't disappear. Conservation laws, things stay put. The total mass doesn't change, for example. So here I want to illustrate one example of a symmetry and try to get your help in solving it. So here we have two containers, one green container, one white. We take a glass, we fill it with some of this green container, green paint, pour it into the white paint, and then we stir it nicely. And then we take the same amount, but now from this mixture, and pour it back into the green one. And then we mix it. And then we put it down. Yes, please go down. The glass is stuck there? No, it goes down. Good. So the question that I want to ask you is, which of these two containers has more mixture of the other one? In other words, does the green one has more white in it, or the white one has more green in it? Is the question clear? Okay. So those of you who think the white one has more green in it, raise your hand. Okay. Those who think the green has more of the white, raise your hand. Nobody almost, very few. And those who think they are equal, raise your hand. Okay. So, very good. So here, many of you thought that the white one has more green in it, and that is the intuitive answer, even though it's not the correct answer. Let me explain why it's the intuitive answer. It is the intuitive answer because when you poured from the green to the white, you took pure green, but when you took it back, it was mixed. So you're bringing some of the white back to the green. So therefore, the green is more in the white than the other way. That's the logic. But that's wrong, actually, it turns out, even though it's intuitive. Here, I want to use symmetry to show you that this was a mistake. What is the symmetry here? Well, to begin with, they had equal volume. There's a symmetry between the left and the right. At the end, they still have the same volume. Okay? Clearly, because we took the same amount back and forth. The total amount of green is equal to the total amount of white. So whatever in this mixture is not green must be white. And whatever in the white must be, which is not white, must be green. But since the total volumes were equal, if you switch them, they must be back to the original one. So they must be equal amount of mixture. So the answer is they are equal. And so if you think about it this way, you can kind of unmix it and kind of imagine unmixing them, and then you will switch them, put them back in the right place. So this kind of shows us that the conservation, that the mass does not disappear, and the symmetry between them kind of explains and deconfuses us. So sometimes symmetries are powerful, even though in this simple example that you see how it works. Now, symmetries are fun, but it turns out in physics, breaking them is even more fun. Now, breaking symmetries can be done artificially. I'm not talking about that. I'm talking about the notion of spontaneous symmetry breaking, breaking by itself. Now, you might ask, what does breaking a symmetry by itself mean? Our next puzzle illustrates that. So again, I want your help. We have 4 cities at the corners of a square. The cities are A, B, C, D. We want to build a highway system connecting these 4 cities in such a way that it is the shortest length of the total highway system, because it costs money, and we want to minimize the cost. Okay, the question is which highways, and moreover, we want to be able to go from every city to every other city. Not necessarily directly, but through some path. Is the question clear? How many of you think the shortest highway system connecting every city is this? Raise your hand. How many of you think it is this? Raise your hand. How many of you think it is this? Raise your hand. How many of you think it is this? Well, this is the same, more or less. I shifted it down, so this is cheating. How many of you think it is this? Raise your hand. This turns out to be the answer. This looks crazy. This looks crazy because why does it look crazy? It looks crazy because it does not have the symmetries of the square. It has some of the symmetries, like the reflection A and B to C and D, but the reflection between AC to BD is lost. Namely, the reflection around the diagonal AD is lost. So if you reflect around that diagonal, you get a different system. What that means is that if you lived in city A, you can get to city C much faster than from A to B. So you have broken the symmetry. Not artificially, but by minimizing something. In physics, this happens, and what we minimize is the energy. So when you minimize the energy, even if you start with a situation that you had a symmetry, the minimum solution might break that symmetry. This turns out to be extremely important in physics. In fact, there's an example of this appreciated by the Greek philosophers already a few thousand years ago. And this is the way they reason. They had already, these Greek philosophers were very smart, super smart. They had already figured out that the earth is round. Now, they had noticed that the earth doesn't move. Like, it doesn't seem to move. So they wanted to understand why it doesn't move. Now, why would they think it should have moved is that they looked at the sky, the sun was moving, the moon was moving, everything was moving, but the earth wasn't moving. They wanted to explain why is the earth not moving. So they said, well, the reason it's not moving, this was their reasoning, is that the earth is at the center of the universe, and if it were to move, it would have to pick a direction. And picking a direction breaks the symmetry. So if it goes, for example, that way, you have broken the symmetry. And therefore, since the Earth does not want to, since the symmetry is there, and symmetry breaking is a bad thing to do, that's why Earth does not like to move. That was their reasoning. In other words, they say it's forbidden. You cannot move because it breaks symmetry. So their idea is very much ahead of their time. We use these kind of thinking even today about trying to explain physical phenomena using symmetries. But even then, Aristotle found a flaw in this reasoning. He said this is not a good reasoning. And to convince people that this is not a good reasoning was the following. He said, suppose you're at the center of a circle and you put food around the person, around the circle. So you're at the center of a circle and the loaves of bread is around the circle. Okay? Is that clear? The question you ask is this person going to move? Is he going to move? Of course he's going to move. Otherwise he's going to die of hunger. But it breaks the symmetry. He has to choose a direction. He does not care. He breaks the symmetry. Breaking the symmetry is a matter of life and death. He will break the symmetry to get the food. Is that clear? That's what happens. Even though the problem was symmetric, the solution breaks the symmetry. This is the origin of how Higgs particle, this famous particle which gives mass to everybody, including all of us, gets its mass. It's through such a mechanism, what we call the spontaneous symmetry breaking. So it's a very deep but simple physical idea. In fact, your bodies break symmetry. You might say, what? My body breaks symmetry? Yes, your bodies. Each time you go in front of the mirror, you should pay attention. You break the symmetry. How is that? Well, we live on the Earth, which has more or less, on the average, 360-degree rotation, horizontal rotation symmetry, right? So, and we have evolved on the Earth. Therefore, we should be rotationally symmetric, 360-degree symmetric. But, for example, our eyes are in the front. It is not like this. So each time you go in front of the mirror, you should remember that your body breaks the symmetry. Now you might ask, why does it break the symmetry? Well, I think it might be because, we had to go after the food. You see, we have to know where the food is. And we have to go after it. We don't need to go over all the circle. We need to go in one direction. In other words, the movement breaks the symmetry. What's the evidence I have for this? Well, on the average, trees are more symmetric. Right? Trees don't have to move. So it's consistent with that picture, that they are more symmetrical in terms of rotation than us. So your body spontaneously breaks the symmetry. And that's related to how you get your mass. So that's a kind of a cool connection. So as I said, it explains the origin of the mass, the Higgs particle, why there is more matter than antimatter, how the magnets work, and how the superconductor works. All of these are related to spontaneous symmetry breaking. So breaking the symmetry automatically has a lot of interesting physical consequences. Now, mathematics is really powerful. Now, you might think that you have to go very complicated math to have a really cool applications. Here I want to illustrate that even simple elementary school math could be interesting. We don't need to get too fancy. Math is interesting and it deconfuses us. So let me give you an example. Consider the Earth and the equator, and consider a belt around it, like this is a belt around the equator, and suppose you open it up. So you open the equator belt and it becomes this length down here. And then you add 1 meter at the very end. So it's a huge belt. You add 1 meter to the end. And then you wrap it around the Earth again. But now it's not going to be tight. It's going to be a little bit above, right? The question is, how big is this? How much does it come? What is this X? How many of you think it is like a half a meter or more? Raise your hand. How many of you think it's 1 centimeter or more? Raise your hand. How many of you think it's less than 1 millimeter? Raise your hand. Okay. Okay, I guess we have more or less covered the possibilities except between millimeter and centimeter. The answer turns out to be 16 centimeters, which is surprisingly large. But it's actually a simple math, elementary school math. Namely, the radius was 2 pi r if the radius of the Earth is r, and you added 1 meter to it. And that should be 2 pi times the new radius, which is r plus x. And so you find that 1 is 2 pi x, and x is 1 over 2 pi, which is 16 centimeters. Surprisingly large. However, the shock is yet to come. This is not the shocking part. Suppose we take this here, this part of the belt, and pull it further to the left, so that that side is tight, but this can go more. Right? We can push it further out. The question is, if you do that, how much further does it go? How many of you think it's going to go up to a meter? Raise your hand. Or half a meter, let's start. Half a meter. Okay. How many of you think it can go up to 2 meters? Raise your hand. No. 120 meters, raise your hand. Absolutely not. Well, yeah, it is 121 meters. How do you know this? Well, just this needs a little bit more than the elementary math I showed you. It just needs calculus. Just expanding sines and cosines in power series, you can immediately get this formula. I encourage you to check this formula. It's 121 meters. Unintuitive. So simple looking things can actually be very surprising. So our intuition is not necessarily good. Somehow our brain is not wired correctly to get these correctly. But math is a way to clean up our thinking. So it's very important. Another thing is that you don't have to get to deep, complicated math. And one particular example is continuity. One of the basic facts and important things I would say about topology is the notion of continuity. Basically, in physical terms, means things don't jump. They gradually change from one to the other. The physical laws and all that share this property. We don't have this jumping situation. We always have something smoothly goes from one to the other, or at least continuously changing from one to the other. So continuity is an important principle in physics. I want to give illustrations of this principle. Again, we go back to the Earth. Again, consider the equator. Here we are trying to describe the weather on the equator. So we want to measure the temperature on the equator. So you open up the TV, they're going to say, today we measured the temperature on the equator. Okay, it's a boring thing, but somebody might do it. And of course, the temperature varies across the equator. It's not necessarily a constant. And then you ask the question, could it be that magically there are at least 2 points opposite relative to the Earth which have the same temperature? Exactly the same temperature. Well, it could. Why not? The question is, does it have to have a situation like this? In other words, suppose we only assume that the temperature varies continuously as you go around the equator. does it have to be the case that there are 2 points opposite to each other on the equator with the same temperature? How many of you think the answer to that is yes, there will always be such points? Raise your hands. How many think it doesn't have to? You can arrange the temperature so it doesn't have to be equal at opposite points, at some pair of opposite points. Okay, the answer is that there always is 2 points opposite to each other which have the same temperature. And how do you see that? Well, suppose they are not equal. Consider a function which is the difference of temperature across from each other. There's a function f, okay? This function is defined on every point on the circle. Namely, you take the temperature on one point minus the temperature on the opposite point. Is that clear? If this function is ever 0, that means the temperatures on opposite points are equal. Is that clear? So all we have to show is that this function vanishes somewhere. But that's the way to think about this, that suppose you start with this and it's not 0 here. If you go to the opposite point, it flips the sign, because if you flip the order of these two, you get the opposite sign. In other words, if you go to the opposite corner, f flips its sign. So no, in other words, wherever you start, if you start with negative, on the opposite point you get to the positive, and by continuity it has to cross 0. So continuity shows there is a 0, and therefore there are equal temperatures. So this is a simple application of topology to physics. Namely, we're interested in temperature. The physical law tells us temperature varies continuously, and the simple mathematics tells you that temperature has to be equal at some point to the opposite. It does not need any deeper physics than continuity. So continuity is a basic principle of mathematics and physics, and it's very powerful. Another example is, if you measure the temperature and pressure on the Earth, there turns out to be at least 2 points opposite to each other on the Earth, relative to the center of the Earth, which have the same temperature and the same pressure at any moment. It's quite remarkable. It just follows from the topology of a sphere and the continuity of these two. Now, I will give you another example of the power of continuity. This is really cool, but unfortunately, the mathematics of it is a little bit more complicated. It has to do with gravitational lensing, which is one of the features of general theory of relativity. So if there's a galaxy here, and if we are here on the Earth, and we are watching the galaxy, the light might come from different paths and get to you here, and the way this would work is that the light is getting bent by gravitational force. Einstein told us that the gravity can act on the light, and the light, by geometrical curving of the space, it could cause the light to bend. So if you're here on the Earth, you will see 2 images of this galaxy. So you can get multiple images. For example, in this picture, this region has repeated objects. For example, these 4 objects are the same quasar. And these 3 galaxies are the same, the orange ones. So it's quite remarkable. You're looking at the sky and you think you're looking at different objects, but some of them might be the same. It's just the light comes out different ways. You might be puzzled here that there are odd number of images here, 3, 5. Is that always the case? Do you always get an odd number of images? This is a fact. It turns out the number of gravitational images, if no image is blocked, of course you can block an image with your hand or something. If you don't image, if the light doesn't get trapped in a black hole, or if you're not blocking it, then it turns out you always get an odd number of images. And precisely less than half of them are inverted. So the 5 I showed you 2 of them are inverted images. They're not like this, they're flipped. And 3 of them are straight. So always, less than half of the images are inverted. Now, how do you do this? How do you show this? Well, you solve the Einstein's equations. Well, that's too complicated to solve and show. It turns out you can prove this using simple ideas from mathematics. The topology and continuity shows this. How does that work? Well, there's this notion of a degree of a map. Degree of a map is basically, if you have a map from one space to another, you look at the pre-images of one point, and you ask how many points go to that, how many points get mapped to it. And then you count the number of pre-images with a plus or minus sign, depending on whether the orientation of the map is flipped or not. It turns out that the degree of the map does not change under deformations of the function continuously. So the degree of the map is what mathematicians call is an invariance of that map. You can count it, and it's going to be there as a number, which is always that, as long as your map is continuously deformed. So here, if you look at the situation, for the moment, suppose you turn off all the galaxies. Turn off all the matter. So there's a galaxy here, and you're over here. The light goes straight out if there's no gravity between us. So if you take a sphere near the galaxy, there is a map from the sphere near the galaxy to a sphere which passes through the Earth far away by just following the light ray. The light hits the first sphere at some point and hits the big sphere at some other point. So that's a map from the small sphere to the big sphere. If there is no matter between us, the degree of that map is 1, because it's an identity map. It maps every point on the sphere to the corresponding point. So the degree is 1. However, if you now gradually turn on matter, this function changes continuously. But the degree of the map cannot change because it's a topological invariant. So the degree of the map is always 1. So the number of images can change, but not the net number. The net number should always be plus 1. So if you get 3 images, then you must have 2 plus 1s and 1 minus 1. In other words, 1 of them should be inverted and 2 of them should be straight. So here you can illustrate it. This is trying to illustrate how that happens. So here you see this Earth. The geometry of the region is effectively, what I'm saying is that you can think about the geometry of the region of the imaging is flipped or curved like this. So here you only have 1 line passing. Oops. So here you see, for example, 1 image. And if you continue this, over the next one, over here you see there are 3 of them. One of them is inverted in the directions as you go around. And over here you get 5, and so on. So you always get these odd numbers. And that's related to the degree of a map. Now, but sometimes you need to get abstract. And sometimes you need to think abstractly. And mathematical abstraction is one of the powerful things we deal with in physics all the time. So here, I'm going to give you a puzzle. The puzzle is about ants. 4 ants on a plane. They are marching. The ants are marching at a constant velocity in different directions. So in other words, their speed is constant, but their directions are not the same, and each one might have a different speed than the other ants. What we know is that the ants collide with each other. All of them, we know they go through the same point at the same time. Except for ant number 1 and ant number 2, we do not know if they go through the same point at the same time. In other words, we have a situation like this. The ants are moving. There are 4 of them, and 1 and 3 cross. And the question is, this ant number 1 and 2, as they come here, are they going to cross? Will they collide? How many of you think, yes, they have to collide? Raise your hand. How many of you think it does not have to collide? Raise your hand. Okay. It turns out the answer is they have to collide. But how do you show this? It turns out you have to use abstract mathematical thinking. What's this problem? Abstract mathematical thinking? Yes. You have to introduce an extra dimension, like in string theory. But actually, more specifically, like what Einstein did. Time is also a dimension. So this problem is not two-dimensional. This problem is three-dimensional. 2 space and 1 time. Why does that help us? Well, the ants are going at a constant speed. So if you project them into looking at it and where they are in space and time, they look like straight lines. So the ants are going on straight lines in space-time. Is that clear? So you have 4 ants. Each ant is going to correspond to a straight line in 3 dimensions. Is that clear? Moreover, we know that out of these 4 lines, all pairs cross. Why is that? Well, because they pass through the same point at the same time. That means the corresponding lines in 3 dimensions cross. Then 3-dimensional Euclidean geometry can be used to prove the other 2 have to cross. And how does that work? Well, let's see. You basically introduce time, and now they are marching in space and time. So you see the planes. The ant 1, 3, and 4 form one plane. The ants 1, 2, and 4 form another plane, but that plane includes the lines 2 and 4. Therefore, the lines 1 and 2 should be on the same plane because they're both on the plane 2, 4. So Euclidean geometry shows that 1 and 2 are in the same plane, and since they were going in different directions, they have to cross. It's just that. So abstraction allows you to solve it without doing any other work. Duality. One of the fascinating things in string theory is dualities. Duality means things that look one way might look completely opposite, and they would be equivalent. For example, like this drawing by Escher. You see, if I ask you, what is this the drawing of? You could say this is a drawing of a day in a white sky with the black birds flying to the left. If you looked at the other side, you say, no, this is the story of white birds flying at night. If you look down here, you say, no, there's no birds here. They're just the fields, farm fields, black and white farm fields. Of course, they are all correct. Depends on where you're looking at. What we call is that we say there's a duality transformation taking you from one perspective to another. This is exactly, in spirit, what we do these days in string theory. Okay, how do we have a puzzle about this? Are you ready for this puzzle? How many of you like ants? Good, thank you. This is going to be the next puzzle. It's again about ants. We have a wire, actually not a wire, a ruler, 1 meter long, and we have a bunch of ants on this 1 meter long ruler, and they move with the speed of 1 centimeter per second. Now, they go at a constant speed, and when 2 ants meet, if they collide, they reverse the direction and they go the other way until they meet the other ant and they collide and they go back and forth. Is that clear? But if they get to the end of the ruler, they fall down. I'm sorry, but the ruler is only 1 meter long, so if they continue marching, at the end they just fall down. Okay? It's like this. So You have these ants, the blue one hits the orange one and then goes back, and then purple one and so forth, and when they get to the end, they fall down. At the end, all of the ants will fall down, unfortunately. But there's a puzzle for you. Where do you put the ants at the beginning, and which direction should the ants initially move, to the left or to the right, so as to maximize the time that the last ant is on the meter stick? Is the question clear? How many of you think a good strategy is to try to put all the ants towards the center and instruct them to go opposite, left and right, relative to each other? Raise your hand. How many of you think it doesn't matter where you put any of the ants? Raise your hand. How many of you think it doesn't matter where you put any of the ants except for one? Raise your hand. Okay. Well, it turns out that indeed the answer is it does not matter where you put any of the ants except for one. Why is that? Well, the reason is that we should not be looking at colorful ants. We should look at the ants in their natural color. What is the natural color of an ant? Black, thank you. So here I'm confusing you. I should draw black ants. So if I draw black ants, what happens if two of them collide? Well, they go the other way. But really, can you see the difference between the ants colliding, going back, and not colliding? Like, are they going through each other, or are they colliding and going back? There is no difference. That's a duality transformation. In other words, when the ants are colliding, instead of reversing direction, we can do a dual transformation to flip the identity of the ants and continue marching. Therefore, if you want to have the ants last the longest, you put one ant at the very end and say, go to the right, and that's the maximum you're going to get. That's it. It's not going to be that ant that survives. Some ants will survive the longest, namely 100 seconds. So I'm coming to the end of my talk, but this is going to be my last puzzle, which in fact is my favorite puzzle, because it teaches us about the methodology of science and scientists. This one, we are going to be all scientists now for this puzzle, and we are going to do experiments together. In science, we take examples, which means experiments. We do experiments. We then formulate a general principle based on these examples, the laws of physics. We predict what the laws of physics are. And then we come up with explanations why these laws work the way we think they do. And then, of course, we again go back to first one and step one and still do the examples, meaning we never stop doing experimentation, just to make sure we didn't make a mistake. This is the scientific methodology. Is that clear? So let's do a scientific experiment together. The experiment we want to do today might sound a little boring, sorry. The experiment is we take a circle and we consider points on the circle. If you take 2 points on the circle and you connect them, how many regions do we get in the circle? 2, thank you. So 1, 2. Good? So if you have 2 points on the circle, when you connect them, you get 2 regions. Suppose you take 3 points and you connect those. How many regions do we get now? 4, thank you. So 1, 2, 3, 4. In other words, 2 points, 2 regions, 3 points, 4 regions. Look for patterns. That's what science is, looking for patterns. We are doing experiments. The next experiment. We add one more point, 4 points. How many regions are we going to get now? Excellent, 8. 4 points, 8 regions. Do you get the pattern? How many of you think for 5 points we are going to get 16? Raise your hand. How many of you think we're going to get 15? Raise your hand. How many think we're going to get 17? Raise your hand. Okay, let's check it. The 5th point, we did experiment. We count 16. 2 points, 2 regions. 3 points, 4 regions. 4 points, 8 regions. 5 points, 16 regions. Why are we getting this? It's doubling each time. Why do we get doubling? The reason we are getting doubling might be that each time you draw a line, the region is either to the left or right, so there's a factor of 2 each time. That's it. So how many think if I have 6 points, I'm going to get 32 points, 32 regions? Raise your hand. Some people doubt that. You guys are super smart. Because if I do the next one, we end up getting 31. So it does not work. It does not work. It fails. We had the theory. I explained to you the theory. It is a wrong theory. The theory was incorrect. Experiments showed us it's an incorrect theory. We have to go back to the drawing board and find the correct theory. The theory was wrong. Okay? This happens again and again in science. We think we understood it. We do more experiments. It doesn't work, and we go back and find a better theory. It turns out for this one, the theory has actually been solved, and there's an answer, which is the number of regions goes like 1 plus n choose 2 plus n choose 4. And if this continued, if it didn't stop at n choose 4, you get a power factor of 2 each time. But since it stops, it gives you a different answer. So I've run out of time, so let me just say I hope I have conveyed the power of simple mathematical ideas in the context of physics. And there are many more examples like this in the book. Even the most advanced ideas in physics have simple mathematical underpinning, just like the puzzles we have discussed. Thanks for listening to my talk.
Yeah, thank you very much, Professor Vafa. That was a lot of fun. Questions from the audience now. We can take a couple of questions about the book or the presentation. Yes?
Thank you. What are the limitations of existing theories and why it is necessary to propose a superstring theory? Thank you.
The exact limitations of the theories is that in the context of string theory is that we do not know what is the fundamental formulation, what is the basic laws of it. But more generally, I believe none of the laws of physics today are exactly correct. In fact, I believe that this is going to be always the case, that we are always going to find the analog of improvements of the laws. We are never at the end of the road. So all the laws are in some form approximate, and we have to figure out how to improve them. String theory is no exception. Of course, string theory is the most advanced understanding we have of fundamental physics, and in particular of how quantum theory and gravity can be put together.
More questions?
Over there, there's a question.
There is. Yeah, maybe you can put. Yeah, there. Next.
Good afternoon, sir. I'd like to ask a question. A photon is a boson and an electron is a fermion. Why is it possible to release a photon which is a boson during an electron energy level transition? Is it energy that to a photon?
So just to make sure, when we say electron jumps, the electron doesn't disappear. the electron goes from a higher energy to a lower energy, and it emits a photon. So a fermion can go to a fermion and a boson. In other words, the total fermion number, mod 2, is conserved. So you start with one fermion, you ended up with one fermion and one boson. So this has to do with the property of the spin of the particles. Fermions have half-integer spins, and so half-integer numbers added up together, mod 2 is conserved, and that's the conservation of the number of fermions, mod 2.
Okay, thank you.
You're welcome.
Other questions? Yes?
Thank you. Sir, may you explain the laws of symmetry with group theory and the Noether's theorems? What does that have to do with our, like, the conservation of energy and the conservation of mass?
Yes, so symmetries and conservation laws are related, surprisingly, I would say. So the fact that if you consider physics at one place and move and do an experiment physics over here, turns out to be related to conservation of momentum. The fact that if you do the experiment today and repeat the same experiment tomorrow, the fact that the result doesn't change implies the conservation of energy. The way this works is through Noether's theorem, which tells you when you formulate physics in terms of minimal action principle, least action principle, that formulation leads you to connect symmetries to conservation laws.
Okay, thank you.
Yes?
Hi, nice to meet you here, Mr. Vafa. I'm a student from Tsinghua University High School, and my question is, what is the current research at the forefront of mathematics, and how do these studies help the development of human beings?
Well, mathematics is a huge subject, and of course, I'm not a mathematician, so probably you should ask Professor Yao this question, but I think math is a huge number of areas, and it applies to all sciences. So not just physics. And so it's a general framework to address things which you can quantify or have a framework for theoretic ones. Math typically is its answer. So which one is the forefront of it depends on which question you're asking. I would say that's probably the most exciting thing about math is that all math is useful for something.
I mean, how does the highly abstract mathematics drive concrete production?
Well, I try to give examples. For example, you remember the example of the ants? Or the example of the number of gravitational images? Those are abstract mathematical statements. But they have concrete meaning. The photographer of the galaxy sees 3 images. Say, why 3? Why not 2? Why not 4? Why are they inverted? So they will understand what they are seeing. So mathematics helps you put into place what our understanding is. A good way to summarize our learning and formulate our expectations about reality.
Okay, thank you. Thank you very much.
Over here.
Okay.
Here, there is a question there.
Yeah, okay.
Thank you for this funny talk. And I'm a math student, and I want to learn something about physics. And so I wonder if math students want to know something about physics and our universe. Can you give some advice or how to study or some?
Well, studying, there are standard textbooks in physics.
Oh, I know that. So
you're asking about which textbooks, or what is the?
Yes. Because if you are like you don't learn math, I think when you study physics, you may have to like read more books. But if you study math, I think
yes,
it will help you. Like
absolutely, you have to study them both.
Okay.
I think the thing that I cannot overemphasize is that one without the other for explaining reality doesn't work. Physics you have to learn. Math you have to learn, and trying to mix them is a great idea. So I think we have learned from history of science and history of physics in particular that math is an effective tool in solving or formulating physical laws. Of course, physical laws and their formulation have developed math too, like Newton's development of calculus is a very concrete example. It's still going on like that in string theory, where we are developing new mathematics.
So their connections is like strengthening, like there are more and more connections between.
Yes, the connections are building up. New branches of mathematics are being developed in the context of physics because we have questions that we need mathematical help. So we have mathematical frameworks to build and address those questions, and vice versa. The ideas that come from physics suggest new mathematical structures that people had not studied.
Okay.
Maybe one last question.
Hello, Professor Vafa. I want to ask a question. Since you cannot observe the string, yes. What makes you think of maybe the atoms is actually a string? What kind of phenomena makes you think of?
Good question. In other words, you're saying, and I should have emphasized, that we don't have experimental observation of strings yet. So we have not seen actual strings in the laboratory. So what makes us so sure that they exist? The reason we think it exists, we cannot be 100% sure because we have to ultimately see in experiments. The reason we think it is the case is that over many decades, people have tried to understand quantum aspects of gravity, and it hasn't quite worked. Strings automatically give you answers which are finite and make sense with gravity. A very surprising, rich structure. We don't believe such a rich structure exists without its being true. More than that, it incorporates all the physical pieces that we think it should be there, like forces, gauge forces are there, unification of them with gravity is there. A lot of these features are there. So both aesthetically as well as connections with what we already know suggest that they exist. But of course, experiments are the final judge, and we have to wait.
Okay, thanks very much. Let's thank Professor Vafa once again. And next, let's welcome Professor Leslie Valiant to the stage. Yeah.
Okay, well, good afternoon. So